measuring errors. So what's an error? Yes. Okay, so how far we are off from an actual value, for example, right? Okay. Yeah, that's true. So what your colleague defined is what we call the true error. And the true error is defined as the true value is the difference between the true value of a quantity and an approximated value. Okay, does that make sense? So you do an approximation on something, and you know the true value, you take the difference, that defines an error. True error is also sometimes called absolute error, okay? Now don't confuse that with the absolute value, because typically we always take the absolute value of the error. So when we say absolute error or true error, those mean the same things. That's an approximate value minus a true value of a quantity. So when I call this capital E subscript t for true value, so ET is true value minus approximate value. And again, often we report the absolute value of the true error. So let me give you an example. The first derivative of a function can be approximated as f prime of x approximately equal, so given a function f of x, so this could be exponential, could be sine, whatever, is given by f of x plus h minus f of x over h, where h is some small number, okay? Now for the function f of x, 2 times exponential to the 0.5x, find the true error in evaluating f prime of 3 using h equals 0.5 and 0.05. Okay, clear? Is this problem statement clear? So we have a function 2e to the 0.5x, okay, and we want to evaluate the error in approximating its derivative using this formula. You should be familiar with this definition of the derivative. You took that in your high school, okay? So we will come back to that later when we learn about differentiation. Okay, solution. Well, obviously we need the true value, right? So the first thing we need to compute is the true value of f prime of 3 for f of x equal to e to the 0.5x. The derivative is given by, if you cannot evaluate that, we can do it on the board if you want. But essentially, the derivative of 2e to the alpha of a e to the alpha x is equal to alpha a to the alpha x, okay? So in other words, this would be 2 times 0.5 e to the 0.5x, and 2 times 0.5 is 1, right? That's 2 over 2, that's 1. So f prime of x is e to the 0.5x. Now we need to evaluate the true value of f prime of 3, and that's simply given. We evaluate the derivative at 0.3, so that's, so I made a typo over here. So that should be actually, okay, let me fix that on the spot. That should be e to the 0.5 times 3. Okay, I think the value is correct. Okay. Now the next step is to calculate the numerical approximation, and remember we were asked to do that for two values of h, 0.5 and 0.05. Okay, so we start, we just list the true value to remember it, and this is f of x, and the approximation is f of x plus h minus f of x over h. So the approximate value for h is equal to 0.5. For h equal 0.5 is f prime approximate at 3 is f at 3 plus 0.5, right? That's f of x plus h minus f of x, which is f of 3 over h, which is 0.5. Okay, and then you just plug in the numbers. Okay, just do it in a calculator. You can do this in Python if you want, or just on your hand calculator. And now you have the approximate value, f prime approximate at 3 using h equals 0.5, and you can calculate the error, and you get 0.60997. Okay, whatever that value means, we'll criticize this value in a second. Now, from calculus theory, we expect that as h approaches 0, remember the definition of the derivative is the limit as h approaches 0. If you remember your calculus, it's the limit as h approaches 0 of this formula. So we expect that as h shrinks, the error is going to also shrink as well. So now we do the same thing, but for h equals 0.05. And then again, we substitute the value for x, that's 3, and the value for h, that's 0.05 over h. And again, we get an approximate value. and that is 4.53, and then we compute the error, and obviously this error is about 1 order of magnitude smaller than the previous error, which was 0.6. Okay. However, this error does not, this value, this true error, does not tell us how large the error is. So why? Okay, I need a couple of volunteers. Yes. Okay, that's a great answer. Why don't you come up and help me with this illustration here? So I have a tape measure over here, and what's your name? Eric. So Eric, I'd like you to go and measure that table using this tape measure. I'm gonna go and supervise the measurement. In the longitudinal direction. Okay. Okay. So let's see. Get 57.5 inches. What if I tell you that the true value of this, the length of this table is 50, we said 57.5, let's say 58. So we committed an error of 0.5 inches, right? Now I want you to measure my phone. Let's see. Oops. Oh, of course, not gonna work. Always beat it.
Trick, yeah.
Old engineering trick. You know where that comes from? That comes from vacuum tube. Get loose, the electronics would get, so you'd go beat on the TV a little bit and would kind of put it back in place. Okay, so it is locked. Okay, there you go. Okay, let's try to measure it. So okay, hold on. So with the error here, the true error was 0.5 inches. So the table was, his measurement was 57.5, and according to spec, when I designed, when the carpenter made this table, it was supposed to be 58 inches. So there's an error of 0.5 inches, okay? Now, what did you get for the phone?
5.5.
5.5, but what if I tell you Apple designed this phone to be 6 inches, okay? So we committed also an error of 0.5 inches. But which error is worse? So in both these measurements, the error is 0.5 inches. The true error is 0.5 inches. It's identically equal. But which one is worse? The error on the phone. Why? Yeah, because 0.5 inch error on the phone has a much larger portion of the phone compared to the size of the table. So it's like saying you're measuring a 100-meter bridge and you commit an error of 10 centimeters, and then you measure one of the suspensions, which is 10 meters long, and you commit an error of 10 centimeters or 1 meter. You know, which one is worse? It depends on the size of the quantity that you're trying to measure. Thanks, Eric. Okay. So is that clear now? The absolute error doesn't really tell you how large or how bad it is, because it doesn't take into consideration the scale of the system that you're measuring. And I'll give this example. A 1-foot error in measuring a 1-mile bridge is insignificant compared to a 1-foot error in measuring a 10-foot table. Does that make sense? So what we need is a measurement is to take this error and actually make it a proportion of the true value. So all we need to do is take the true error and divide it by the true value. And that gives us what we call the relative true error. And the relative true error, or the relative absolute error, is essentially a measurement of the size of the true error with respect to the true value of a quantity. And that's defined as the true error over the true value. Okay? So now we can measure these two errors, the 0.5 inch error over 58 inches versus 0.5 over 6 inches. Okay? And you will see that the error in the phone is much larger than the error in the table. Okay? Now, oftentimes, because we're measuring a proportion, we report a percentage. Okay, so you're vaguely familiar. You should be familiar with these errors. We're just kind of covering things that you already know. So typically, this is how we report our relative error. And notice how I change the symbol now. I call this epsilon t for true relative error, or relative true error, and it's the true error over the true value. Take an absolute value and multiply by 100%. Okay, so that gives you a percentage. Okay, this is another example. A 1 meter error is committed in measuring a 100-meter bridge and a 10-meter bridge suspension. So again, we committed a 1 meter error in measuring the bridge and measuring one of its suspensions. So the error is the same, okay? But which one is more significant? Which one is worse? The solution is to turn this into a relative error. So for the bridge, the true value is 100 meters, the true error is 1 meter, and therefore the relative true error is 1 over 100, or 1%. So we committed an error of 1%. For the suspension, the true value is 10 meters, and the true error is 1 meter. Okay? So therefore, the relative error is 1 over 10, and it's 10%. So although the nominal value of the error is the same, 1 meter in each case, obviously the error in the suspension is much worse. Okay? It's actually an order of magnitude higher than the error committed in measuring the bridge.